Yes, do that. Okay. All right. And of course, now it's going to decide that thing on the top cannot be made to go away. Let's see, control.
Like the little green one. Weird parts that even mine is weird.
Yeah, normally it just goes away. Oh, I didn't look at that. Well, it's a nice capability. All right. Um, I am actively screen sharing. Okay. So the question was, can I explain the Anderson Q lock? Not key lock, Q lock. And it's the idea is you allocate a number of flags, binary values, equal to the number of threads that you want to synchronize. And then when a thread, and then you also have an atomic next pointer. And what you do is you call get an increment on the next pointer. And that gives you your current value. That's what it returns to you. And one plus that, get an increment means first get, then increment. It's like plus plus. There's also increment and get, which is like the other plus plus. Yeah, increment is plus plus. So this is postfix plus plus, and then there's increment and get, which is like the prefix plus plus. All right. So I call get an increment on next, and that gives me a pointer to 0. Now, and the lock is initialized with a true in slot 0. So the first thread to call this method is going to succeed in getting the lock. Okay, and what's going to happen is, you know, it gets that thing, it sees the true, and it says the lock is mine. And now another thread wants to get it. And so what it does is it does a get an increment. And get an increment is going to change that next pointer to point to the third slot, but it's going to return the second slot. It's going to return 1, right? And now it's going to look at 1, and it's going to spin. It's going to wait for that to turn to true. And what's going to happen is it's going to turn to true when the pink processor, the first one to get the lock, when that one wants to unlock, what it needs to do is it needs to turn its own flag to false, and it needs to turn the next flag in the line to true. Yeah, it didn't change it to false. It does need to do that also. But the important thing to enable the red processor to run is to set the next one to true. All right? Okay. By the way, this is the Reagan question class. She's gonna run the whole class for us by asking all the questions.
CLH law.
Yeah.
I understand that it like looks at the predecessor.
Uh-huh.
But I don't understand like how it progresses.
All right. So do you want to give me a slide number?
On 102.
102. All right. All right. So there must be a way to make this go down.
Maybe it's in the more.
I could swear that it was like Alt or something. Yeah, press Alt to show or hide meeting controls, right? So it's just not doing it. Oh, okay. All right. There, you mouse off the controls and then I don't know. All right. So right. So initially we've got a tail that's pointing to false. And we're going to get a get and set on that. So what's going to happen is to acquire, it does a get and set. It's going to put a true in there for thing that's locked. and then it's going to get the other thing back. So now the tail is pointing to true, and the purple lock has acquired this flag that has false in it. And while it's still in that state, we have a red processor that goes and does a compare and set on the tail, and it moves it get and set, not compare and set, does a get and set on that and moves it over another slot. So this is now the way things look. So we've got the purple one had swapped in a node which is purple, and it got back a node which is green. And then the red one got swapped with the tail and got the node that was purple, or swapped in created a node that was red, swapped it in, and got the purple one back. Okay. And so what each one is doing is it's looking at the node that it got back from the get and set, and it's waiting for that flag to turn to false. You with me, Reagan? All right. So this means there's implicitly a linked list between these CPUs. Now it's implicit because no single one has all the things, and you can't really just trace through them in memory, right? It's sort of the pieces are all there, sort of in use. All right, so now the red one is spinning on the purple node, and because you remember our discussion about memory and the bus and caches, it's actually spinning on a cached copy. And because it's spinning on a cached copy, there's very low contention, right? And there's no invalidation until that value is changed. And when it does change, then there is a validation and it gets the lock. Okay. And then red has acquired it. So that's basically how it works. That's how you get the lock.
So is the only difference between CLH and MCS that CLH spins on its own node and MCS spins on a shared node?
You've got it backwards, exactly backwards. Yeah, so what happens is in the CLH lock, okay, so there's another one last piece to this. So let's just keep going through the CLH lock. It's got what is this? Yeah, okay, that's just the Q node. Okay, so it's got the Q node tail, right? It's got its own node. And what it does a get and set with its own node and the predecessor. And then while the predecessor is locked, it spins. All right? Yes. And then the unlock method, what it does is it sets its own node, it sets the locked flag to false. And that allows the next thread in the sequence, which is spinning on this one, to do it to move forward. Okay. And then it updates its my node with the predecessor node. So it's recycling the nodes, right? It's each time it's using a node, it's moving it through the cycle. So the MCS lock doesn't do that
The MCS lock spins
on its own, and it doesn't recycle. But it's because it recycles in the unlock. That's what the CLH lock does. That's why it winds up sharing them. Let me see. Let me pull up my IntelliJ. So I have, I can, um, I can do that. Hold on though.
Where did I put it? Oh, I think I put it in here. Oh, come on.
Shoot, I don't know where I put it. All right, I'm not sure where my official copy is at the moment, but I will go to uh, this one, and you need to see what I'm seeing. All right. So here's the CLH lock. It's got a predecessor node. It's got a current node. It's got the static class Q node. It's got uh, it's got a little counter that I use for testing. So there are the lock and the unlock methods, right? So we get our node, right? And we set locked to true, which is either, this is this is really just sort of signaling our intent that we want to lock. And then we do a get and set with the tail. So we take this node with a true set on it, and we swap it into the tail. And now we take that node we got back, that's the predecessor, and we hold on to it. And then while the predecessor is locked, we yield. Okay. And then in the unlock method, we get our Q node. We set the locked to false, right? Letting the next one go. And then we set my node to the predecessor node. Okay.
Think so.
Does it all make perfect sense now? If you look at it with one eye, it definitely helps. McKay was looking at it like this. Tristan.
So, is there any benefit between using like its own memory and recycling memory?
Well, we talked about that, right? So this is the difference between the CLH, which recycles memory, and the MCS, which does not. And the MCS lock is supposedly better for NUMA machines, which my laptop is not one, right? We have NUMA machines on campus that you could potentially run this on, but usually those are bigger machines than your laptop or your desktop. You remember what NUMA stands for?
Architecture?
Yeah, non-uniform memory address. Yeah. Okay, so you're close. All right. Sorry, Reagan, were you going to say something else?
I think that confuses me is like the release part of it.
Okay. Why?
Yeah.
Hmm.
I don't know. I guess. Yeah.
That's not a question I can answer. Okay. Yes, McKay.
Like that CLH recycles nodes,
Yeah.
but I kind of like I don't really see where this tail comes into play?
So the tail is the place, it's sort of the central piece of the lock, right? So the tail is where when I go to have the lock, all I have is my node. My predecessor node is probably not filled in, or it's filled in with something that doesn't mean anything, right? I have to get the predecessor node from the tail, and I get it by doing a get and set.
Okay, so you set the tail, you get a set back into the predecessor,
Yes,
then unlock, set predecessor.
yes.
This works because there's always one node. There's at least one node that the tail wants to.
Yes. Okay. All right.
What's like, why would you use this one over the MCS law?
Well, okay. So the theory is, right, you have an application with high lock contention, and you can't, for whatever reason, you can't get around that. You're going to have high lock contention. And you want the most efficient, best performing lock for your architecture. And your application is running on the Newman machine.
Just because the Numa architecture.
Yeah. So what you would really do, right, is if this is really your situation, what you would do is you take all these different lock implementations and you would test your application using all of them. And then whichever one gave you the best performance is the one you'd use. I mean, this is a very rare thing for someone to do, but I think it's important if you're going to be a parallel programmer to understand what locks are and what efficiencies and inefficiencies they have and what opportunities they have for performance and so on. In the C++ standard I discovered recently, there is no fair lock. They only have like standard mutex. They have one implementation they give you. It does whatever it does.
Can you walk through how MCS, like the visual part of it, that starts on slide 137?
It's very helpful that you know the slide number.
It's done by staring at the slides.
Yeah. Well, there's also the code, which you have to stare at too. Okay, so we've got a tail pointer, and this time we've got a slightly different Q node structure. So in the previous one, right, the Q node just had a flag in it. This time, the Q node also has a next pointer. So we're going to swap as before, right? And we're going to put our thing in and get something out. And then the red is going to do that as well, right? And the red is going to be looking at our thing, and each thing is going to be looking at the last thing as before, right? And it's going to be spinning on its own memory as before. But this time, instead of an implicit queue, right, an implicit linked list, we've got a real linked list, right? This one is pointing to the next one.
This false.
Yes. So acquired has false there. So the flag is the name of the flag is locked, right? So if it's not locked, that means that it has it. And then it can set that one to false and give the lock away, and then it says yes. Okay, and so the code looks kind of like this. Now, I think, for me anyway, the MCS lock is harder to fit in my brain. I don't know what you think. It's a little harder to fit in because there's some interleaving you have to take into account, right? So we're going to get a Q node. We're going to do a get and set as before. And if the predecessor node is null, I guess we just have the lock, right? That's the other part of this, is the predecessor null in this node. So with the CLH lock, we were always keeping some kind of node in there. In this case, we're allowing it to be null. It doesn't recycle. And And we're going to try to put it back to null after we're done. So what we're going to do anyway is if we get back a predecessor node, then we're going to mark our Q node with locked, and we're going to set our predecessor.next node to the Q node, right? And then we're going to spin on our Q node.locked. So we're going to spin on our own node, right? So in the unlock, what's going to happen is the MCS lock is going to check and see if its Q node has a successor. And if it's got a null, there's two reasons why it might be null. It might be that there is no successor, or it might be that the successor has done the get and set, but hasn't set the next field on its Q node yet. If it's the first thing, if it's the first thing, if it's genuinely the last, if there's no other lock, no other thread trying to get the lock, then it can do a cast of the tail from itself to null, and that should succeed. If that succeeds, that means there's nobody else trying to get that lock, right? If it fails, it means the second thing. It means that somebody else did a get and set, but they haven't yet gotten to setting their QNode.next field. So now we're stuck with waiting for them. We have to wait in our unlock method for the QNode.next to not be null. And once it's not null, we can set our QNode.next.lock to false. And that will allow the next lock to proceed. Okay. Yeah, so there's two possibilities, right? So you look back here, right? And what happens is we do two things. We do a get and set, right? And then after we get the get and set, if the predecessor isn't null, then we set the pred.next field. Now it could be, and this predecessor is whoever got the lock before us, right? Now it could be that when we get this thing back, that that between calling get and set and setting pred.next Q node, we call unlock, right? That could happen. But it also could happen that we get past it. So we have two things to keep track. We have to two situations we have to keep track of. One that there is nobody else after me, or two, there is somebody else after me. They just haven't set their next field yet. Right. So that's the thing that's going on here. So in this case, this is trying to handle the case that there is no one after, right? If somebody has called get and set, then this is already on the tail, then this is going to fail. Right? Yes? Okay. If somebody called get and set, that means that the tail no longer has Q node in it. It has something else. Right? Because
comparing the tails about to Q node.
Yes.
Setting tail to null.
Well, so what it's saying is, right, if tail has the value of Q node, then set the tail to null. So if that means that, and it will be Q node. So after I call get and set, I'm putting Q node in there, right? If nobody else is called get and set, then this will succeed. And that means there just isn't anybody else waiting for the lock. So when I look at QNode.next equal null, I don't know whether anyone else is waiting for the lock just because of that, because there's this time gap between get and set and QNode.next. Okay. So in this case, what I'm doing is I'm trying to figure out what's going on. So if there's nobody else that has tried to get that lock, right, then this tail.cast is going to succeed. And I can return. I'm done. The lock is unlocked. On the other hand, if it fails, that means that I'm in that situation that I just described, where when I checked for null, a get and set had been called, but the pred.next hadn't been set yet. And so what I need to do at that point is I need to wait for that next field to get set. And only after that next field is set can I tell the next node in the chain that it can have the lock.
So it checks to see if somebody's trying to acquire the lock
Right,
first. And if they're trying to acquire the lock, wait for them to.
right.
To like wait for the next thing to until it's ready.
Right. So there's actually a bug in this code. And this is, in case you hadn't gotten the message yet, that parallel programming is tricky, complicated, and subtle, right? This code, as it is on the slides, does not work. The unlock method contains an error. It doesn't set the next field to null when it's done. And so the next time somebody's going back through to try to check for null when it's reusing it, it's not going to be null. It's going to get it wrong. And it can potentially, it'll leave a stale value there rather than cleaning it up.
Like, where is it getting null from?
Well, so that before it puts it into that queue, it's supposed to be null, right? The point is, it's a very simple fix, and I did it when I made the, companion code, right? It's a very simple fix, and you just have to set that queue node .next to null. Oh, this is the right code. So I did it this way because I wanted to set the next field to null before I set the locked field to false. So I saved a copy of the queue node. Then I saved a copy of the next thing, and then I set the next field to null, and then I set next.lock to false. So in any event, the point is, you can test running this code without that clearing, and it doesn't work. Yes, okay.
Yeah, you store next to or set next. But does are you even guaranteed that?
So it depends. It depends on, so probably not. I'm probably not guaranteed that they're in that order unless I make them atomic and volatile. That's a good point. I don't think it's critical that it happens in that order, though. But I would kind of like it to happen in that order, because what I did is I put this assert up here, right? That before I said, it was part of my checking of what I believed was true about my code. I put a pred.next equal null there. And I mean, I suppose if I wanted to, it's probably going to work. If instead of saying qnode.next equal null here, I can probably say, well, no, that won't work. I might be able to say qnode.next equal null here. I might be able to do that. I could try it. But in any event, you have to have that cleaned up. Otherwise, you don't get to the right conditions, So the MCS lock is a little trickier. It's got an explicit queue instead of an implicit queue. It's got a lock-free and unlock method. Most locks have a wait-free unlock method. But this one is special, right? Because it's got that while loop, it's lock-free, not wait-free. Actually, no. Actually, no, it's not. This actually counts as a lock, right? Because if that other thread goes away, it can no longer proceed. Right? It needs that other thread to do that work, or it's stuck. So it's not even lock free. But most of them are wait free. You just set some fields and you're done. But this one's got this while loop, and it's waiting for another thread that better not die at the wrong point.
somehow like a cosmic ray, like right?
Yeah, yes. Well, I mean, things happen. Yeah.
Yeah, so it's only gonna enter that while there's already process.
Yes, it's only going to enter that while loop if there's already a thread in the process of locking.
So it's gonna be theoretically finite. It's not like the other threads in a critical section doing something that it might not have been.
Theoretically, between calling get set and calling qnode.next equals something, the thread could die. You could just not ever get to that second step.
Because it'll depend on the fair schedule.
Well, I'm just depending on that thread to keep running. If it just keeps running, then I'm fine. Never mind about anything else. It just has to keep running. I think it does some kind of round robin, so everything is guaranteed to run again. I don't think I don't think it just does a random thing. I think it's like cycles. So I don't think that should happen. But if something went wrong at the hardware level, right, and that particular thread just couldn't operate, that's a very rare circumstance, mind you. But and we don't really expect that to happen. What we could expect to happen is one of the threads is just arbitrarily slow. But the way to think about it to make it right in your head is what would happen if that thread just goes away? What if it just dies, right? And for lock free and wait free, we are unharmed if other threads die. All right. Yes. That's 4. Yes. All right. So there's these there's these consistency problems, and these were copied directly from my slides.
I'm fine on those. It's fine.
Okay.
I only missed 2 of them.
There are only 2 of them. Okay. All right. It's the next part. Okay. Everybody's cool on the first 2 questions there?
Yeah.
Okay. All right. So the next one is, what is the consensus number of each? And your choices are 1, 2, or 3 or more, right? Regular memory is 1. We know that. We spent a class proving that. A wait-free queue, that was another example we did in the slides. If you have a wait-free queue, you can use a red ball and a black ball and figure out consensus 2 with that, right? If you do an atomic write to 2 of 3 memory locations, we figured out that we could also solve consensus 2, right? Let's see, an RMW instruction that adds to a register. So addition commutes, right? So that's 2. An RMW instruction that exclusive ORs the register. Well, exclusive OR also commutes. So that's also 2. And the get and set instruction we said was 2. And a RMW compare and set instruction we said was infinity. And we had an example for that. What did you do?
Wait, review.
Mm-hmm.
I thought we figured out that wasn't possible based on the slides.
What we figured out in the slides was that you can't build a wait-free queue without an RMW instruction. But if you have a wait-free queue, you can solve consensus, right? So we actually showed that if you had a weight-free queue, you could solve consensus. And we used that to prove, and that was the step in our proof that said, therefore, you can't build a weight-free queue without an RMW instruction. But you can build one with one. If you have an RMW instruction, you can build a weight-free queue. Yes, Tristan.
If an RMW instruction doesn't commute, would that be reconsistent?
If RMW, yes, if it does not commute, then it's going to be 3 or more,
3 or more.
right? It's almost guaranteed to be 3 or more.
Non-atomic, so that's just saying that you're using regular memory, basically.
Atomic write. So a non-atomic write means some thread can see that so, between writing one thread. So if one thread is reading and one thread is writing, it's possible for a thread to see one of those locations written before the other one is written. That's what non-atomic means. It didn't happen all at once. There's time gap in which something else could happen. So a non-atomic write, maybe I didn't say that when I went through it. So a non-atomic write of 2 or of 3 memory locations is really just regular memory, which we already determined was 1. Okay. All right. You have more questions? We've got people who haven't asked me anything.
I have a question. When are we getting our participation grades in?
There should be a bunch of them. Isn't there 3 at least?
Chapter 3 and chapter 5 are when?
I haven't entered those?
No.
All right, I'll have to go back and check. I thought I'd entered those. So we have this class and next class to just review everything, right, before the midterm. There is a lot of stuff. Well, it's a college course, you know?
Well, how did we show consensus too for the wave free queue? I'm kind of confused by the red black ball.
Okay, so what we do is we initialize the queue. We put a red ball in the first slot and a black ball in the second slot. Now we have 2 threads because we're solving 2 consensus. So each thread tries to DQ a ball. Maybe it happens almost at the same time, right? But the nature of the queue is only one of them gets, it's got to behave consistently. So one of them gets the red ball and one of them gets the black ball. Now, before they try to DQ the ball, there's an array of 2 things called the proposed array. And each thread writes the value it wants to propose into the array with its thread number as the index. I can pull it up. Bregan, do you know the slide number?
Let's see. What was the rating? Red ball and black ball.
Let me just pull up the chapter and I'll just show you the thing again.
If I'm able to recreate it, I mean, they probably
68.
Slide 68.
So there's an array. We have 2 threads. That means the array is only like 2, 0, and 1.
Right?
So you have the thread.
Right.
There's a proposed value, and that's where we stop.
Right. So we have the proposed array. We have the FIFO queue. Each takes its value and writes it into the proposed array using its thread number, which is going to be either 0 or 1 as an index.
Values.
So there's the proposed value is So a consensus protocol, right, has some method like propose on it. And it proposes a value. This isn't the way I remember the slide. I want to explain it differently. All right. So the way I like to think of it is you have each thread is going to say like I have a value to propose. Thread one say its value is gold. And thread one its value is ostrich, right? And then both of those methods are going to return an object. And they both have to return the same thing, whether it's gold or ostrich, right? So let's say that thread 0 writes gold into the 0 slot, and thread 1 writes ostrich into its slot, which is 1, right? So that's where it's storing those values ahead of time. Now it goes to DQ, right? And when it DQs, it's going to get one of them is going to get the red ball, and one of them is going to get the black ball. The one that gets the red ball knows that it won consensus, so its value is the one that the method should return. On the other hand, the other thread gets the black ball, and it knows that it lost consensus. So it's going to say 1 minus my thread number is the index I'm going to return from. And so they both return the same thing.
Because I paused the second one in the queue, because the other one was already written. Okay, so I guess what's the wait free part of this?
What's the wait free part?
Wait, I'm sorry, it's just because of
We assert that the queue is wait free. And we show that leads to a contradiction. We actually assert that the queue is wait free, and we say that it's wait free queue built from just regular memory somehow. And then we show that we can solve consensus 2 with it, but we've already proven you can't solve consensus 2 with regular memory. Therefore, the queue cannot be made with regular memory. It
can't exist with the read modify.
It can exist with the read modify write instruction.
I have a general question.
Yes.
So will the midterm have OpenMP and MPI on it?
Yes.
Can you reteach those?
I can go through them again. Yes. That's part of what review is for. Yeah, sure. Do you have a specific
Just like, the concept does not make sense to me
of either thing?
of either thing.
Concept?
The whole entire thing.
Okay, so OpenMP, right? The idea behind OpenMP is you have a bunch of people who wrote codes that are serial. They never thought about parallelism. They never thought about using parallelism to speed up their code. They're just, and they don't want to rewrite their code from scratch. They don't want to go in there and sprinkle locks and things all over the place. And so what OpenMP did is it came up with a way to dress up your code such that it would run in parallel. And the simplest thing that it can do, right, is if you've got a loop, right, you've got some kind of loop that you think could benefit from running in parallel, you put pragma, #pragma, OMP, parallel 4 in the front of that loop. And the compiler will generate instrumentation and such I guess I should mute this. The compiler will generate instrumentation and such around that to create the parallelism. It'll like create a fork of all the threads. It'll give each thread a piece. Each thread will do its piece. Then it'll wait for them all to finish at the end of the loop. Right? That's the simplest way you can use it. But as we know, sometimes parallelism isn't quite that simple. So there's a bunch of other little things that you can do, but they're all done. Well, almost all of them are done by means of these pragmas. So this is the basic model, right? We have a fork join. We have a master thread It runs for a while. It starts a parallel task. The parallel task runs. When it's done, they all join up together, and it just keeps doing that, right? And that's the way it gets its parallel speed up. And these are all the different progmas that you can do, right? So there are method calls. You can ask it, what thread number you have and so forth if you want to do that level of detail. But the basic idea of OpenMP was that you don't do those things, right? You just annotate your code and let it run, and it magically gets parallel speed up. So, oh, and then you use the OMP_num threads variable to control the amount of threads that your application will use. You can tell it to use 1 thread only or 10 threads or whatever. OMP barrier. So a barrier, all the threads have to reach that same spot. So it's like imagine that you're traveling to Florida and there's a Buc-ee's that you all like, right? So the Buc-ee's is the barrier. You're all going to stop at Buc-ee's and wait for everybody to arrive at the Buc-ee's. Then you're going to buy some horrible food that's bad for you. You're going to eat that. And you're going to go on, right? So the Buc-ee's is the barrier, right? The last one to get there is slowed the least, and the first one to get there is slowed the most. But they all have to stop. They have to sync up at that point. That's a barrier. All the threads are going to wait. Whichever thread gets there first is going to wait for all the others. And once they're all there, then they can all proceed again. A critical section means I'm implicitly wrapping a lock around this. So that means each thread will execute the code in the critical section, but it will do it one at a time. It'll serialize on that. And then there's single, and single means that there's a block of code that only one thread will execute, and it will do it by itself. Well, if inside a single, so if you're incrementing a variable with a ++ and you do a single and you have a loop over 10 threads, right? If you have single, it'll increment it by 1. If you have critical, it'll increment it by 10, because each of the threads will increment it as opposed to just one of them. And then shared, private, and first private, you're determining whether the memory is shared memory between all the threads that they can all update, or whether they have a copy, right? If it's private, they have a copy. And sometimes you need to control that to make things work correctly. But that's the basic idea is you just annotate your code with these progmas, and then you get a parallel speed up. And usually if you're programming with OpenMP, you've got a fairly simple code to speed up because it's just big array operations that you're just splitting up. And you generally don't try to do anything complicated like we do in this course, right? You have a very simple code as far as the parallelism goes.
So you not parallel.
Yes, you use OpenMP to not learn how to write parallel code. Well, the other way to think about it is, rather than not learning, right? You've got a big code that you've written before, and you want to get a parallel speed up, but rewriting it would take you the rest of your life, right? Rewriting it properly would take you the rest of your life, and you don't have, or maybe it takes you, 1,000 person hours or something like that, and you just don't have the resources to invest in rewriting the thing. But you could sprinkle some progmas in there and get a benefit. Maybe not. It's probably not going to be as much of a speed up as you would like to have. If you're talking about Amdahl's law kind of thing, maybe you can get 2/3 of your code to run in parallel, and that's better than nothing. So that's kind of the niche that OpenMP is designed for. Tristan.
So the basis out there that use OpenMP
Yes.
I guess like what I'm asking is how often is it used in like a lot of big software? Is it just like
Scientific codes, it's almost universally used.
that would be
Oh, I think I get this now, but what's the difference between this and MPI?
MPI is something totally different. So MPI, so while this is the idea is you can easily just sprinkle these in your code to get the parallelism. With MPI, you pretty much have to rewrite everything. but the idea with MPI is you're actually solving a different parallel problem. So with OpenMP, you're trying to parallelize a code that's running on a single computer. Okay. With MPI, you're trying to parallelize a code that's running on a supercomputer. So you take like any of our so we've got some supercomputers on campus. We've got Supermike, we've got Queen Bee, Queen Bee 4, I guess it is now. And you've got El Capitan over, which I think is the top machine in the world right now. And these machines might have thousands of computer nodes, thousands of things that are like your laptop or your desktop, all wired together, right? And what you typically want to do with something like that is you take a piece of the problem and you put it on each of those computers. And you run that piece of the problem and then you synchronize. And you run that piece of the problem and you synchronize. And you step through the problem that way. And in that way, you can get parallelism, right? So what you have to do to synchronize is you have to call MPI send to send messages or MPI receive to get the messages back. And what Lucas did at the end is he had this Conway's Game of Life. You remember that? Okay, and the idea with Conway's Game of Life, he had this on a cyclic boundary condition. What he did was he had these ghost zones. So these gold zones, so you take the domain that looks like this, that you're playing the game of life on, right? And then you split it into two equal pieces, right? And that's fine, except the game of life, whenever you're updating a cell, so I'm updating that gray cell, it depends on all the green cells, right? And now I want to update that gray cell and it depends on all the green cells. But because of the way I've split this problem up, right, this red grid is on another machine altogether. And I need those values. So what I'm going to do instead is I'm artificially going to add these gold zones onto here. I'm going to have slightly bigger grids. And what I'm going to do between each step of my game of life is I'm going to copy data from here to here and from here to here, right? And that will, so this row of data here is this row of data on the other processor. And I keep that up. And by continuously exchanging these ghost zones, as they're called, I'm able to do a distributed calculation. So OpenMP is for a single node, a single computer, whereas MPI is for many computers. That's the basic distinction. But you can use MPI on a single computer if you want to. It's just not the problem it was designed to solve. All right, I think we should probably do our quiz. All right, so different paper in this.
Get the nice paper again.
Yeah. Well, we got the paper you had last time. Oh, shoot, I may not have enough paper because we have more people than I thought we would have. Yes. Let's see if I.
I volunteer to not take the quiz.
Well, no. You just take the quiz and circle it and hand me the regular copy is what you can do. All right. Who's volunteering to circle things on the quiz itself? Ryan is doing that. All right. So everybody but Ryan gets bubble sheet. Yeah, brilliant. I'll wait for you. Okay.
There's one thing Lucas covered only for like half a second,
Yeah.
but it was towards the end of his lecturing, and we were looking at an Amdahl's law graph of several implementations.
Ooh.
You could see between a hit between threads 9 and 10, there would be a dip before it would go up again.
Threads 9 and 10 of what?
Or just how many threads you're using, how many cores.
Oh, so what happens is, of course, Amdahl's law, when you do those graphs, you get this nice, perfectly smooth thing. But if you actually run a code in the real world, it's never like that. It's bumpy because there's lots of complexity that comes in here. You get different cache effects, and that's hardware dependent, and all kinds of crazy things can happen. You can get some certain number of processors. If you divide up that way, you get a performance boost or maybe a performance penalty. There's just no way to predict these things. I mean, usually.
So on that graph, it's a really noticeable dip just for that one spot, just because of random hardware issues.
Yeah, you can't explain these things. I mean, you have to. That's why you do experiments. I didn't know what I did to my knee, but there's something wrong with it. Okay, we're ready to rock and roll. So after you have your last four digits of your student ID go in the first four bubbles, it'll say that on the quiz.
I don't think I've ever filled out a version other than one.
You must be lucky. I get all kinds of versions.
Well, there's no joy to be had with different versions than A.
Yeah, but I usually get like E, even when I test curves.
But they're all the same.
You've read multiple different versions.
Well, okay, they all have the same questions, but the questions. Well, I developed this machinery for a much bigger class, and it's easier to just use it than to not use it.